So this is where we left off on Wednesday with this kind of notation here. Be careful with the wording, as we talked about earlier in class. You know, if you know someone is female, the chance of them being right-handed is different than if you know someone's right-handed with the chance they're female. So just be aware of those kind of idiosyncrasies. Okay, so here we go with the probability situation. And let's talk through the wording. So this is the kind of wording you'll see in this weekend's homework. And we'll try to be sensitive to your performance and your calculations. So you'll need a calculator today's class also. All right, so let's see here. 81% of households have computers. All right, so I'm going to say that's the probability of having a computer is 0.81. Now, look at this here. 81% of households have computers. Of those 81%, or of those that have computers. So that's of is kind of like key for us as given, which is a conditional probability. So if I know someone has a computer, the chance of having internet access is 92%. Now, what's the chance that a U.S. household has a computer and internet access? So it's a sequence of events. The chance of having a computer and internet access. Well, the first thing, you got to have a computer. Then after that, you look and see if you have internet access. So computing first, then internet access, and then you take the product of those two. Seven, 4, 5, 2. Oh, and look at this. Whereas those of you who were here at the beginning of class, of those 81%, comma, right? And then the rest kind of follows from there. So that's another way to kind of, as a hint of it being a conditional probability. So what we just worked on is the so-called general multiplication rule, where if you have two events, A and B, then you take the marginal probability, multiply by the conditional. And that's the so-called general multiplication rule. And we're saying here that B given A is a conditional probability that B occurs if we know that A has occurred also. Now here's something that's interesting here. Two events being independent. Well, if two events are independent, then B functions independent of A. That's pretty much, or independently, I guess you could say. Making it to an adverb. B functions independently of A. So that's pretty much what we're saying here. B, if you know A has occurred, then B's chance of occurring is the same. It's not affected by A at all. And then I just kind of said it differently. Here's the fact that A has occurred does not, A's behavior does not impact B's occurrence. Okay, here's another example with blood type. All right, and 39% of people are O negative. 2 unrelated people are selected at random with a chance that both people have type O negative blood. So we have the chance for O negative is 0.39. All right. Let's see here. How about, I know some of your names. Andrew. Andrew, right?
Yeah.
Okay, Andrew. I have O negative blood myself. What's your blood type?
A positive.
A positive. So does your blood type impact my blood type? Or vice versa? No? Probably not, right? My blood type's not going to change, right? And you had your blood type before, well, I was around before you were. But my point is that this is a prime case independent events. So sometimes, just by the nature of the problem involved here, you're going to be working with independent events. Your blood type is independent of your neighbors in your row. So we can just assume that we can just multiply probabilities. So the chance of not O negative is 0.61. But in this case, we're just doing 2 unrelated people having O negative blood. So it'll just be probability of O negative for the first person and O negative for the second person. Well, equals the first person being O negative times the probability that the second person is O negative, given that the first person was O negative. And because these are independent events, it doesn't matter, right? Me being O negative doesn't impact Andrew's O negativity, if you will, or not, or it doesn't matter, okay? So basically, in this case, it's just going to be a very straightforward 39% square, which is 0.15 something. $15.21. That wasn't so painful. The O negative notation is a little painful, but overall it's not so painful. Now what we can use is yes.
Why are you multiplying by 0.39?
Oh, here?
Well, you got 0.39 times 0.39 Why did you do that?
Okay, so I have here that this guy is 0.39, and this guy is 0.39, and then why multiply them?
Why is that second one 0.39?
Oh, okay.
Both O negative? That's what it's saying?
Yes. The first person goes O negative, and the second person O negative, because it says here the probability that both have O negative type blood.
What if those weren't independent variables that we need to do something?
Ooh, if they weren't independent, then we would need to know what's the probability of O2 negative given O1 negative. That would be in the problem. So you would have another piece of information. Yes?
Would the probability that one person has O negative and one person doesn't be 0.39 times 0.61?
Ooh, hold that thought. Now hold it. All right? Got to hold it. No peeking ahead at your notes. All right? But that was good. Good intuition. So this is the kind of classroom I like, guys. Good job. Okay. So anyway, I'm getting fired up at 8 o'clock in the morning. Tree diagrams can help us organize our thoughts. Okay, with each stage having a conditional probability, that's fine. You have tree diagrams you can look at. Now, construct a tree diagram for the previous type of blood types. Well, you have this O negative world, And we have what we call not O negative. That's the first person. And then the second person, however you spell person, well, it depends on the first person being in this category or this category. O negative, not O negative. O negative, not O negative. So it's the same kind of model as having a coin. You flip the coin twice, you can have two heads, two tails, heads, tails, tails, heads. So we covered all of our options. Let's go ahead and fill in the probabilities. O negative is 0.39. That's 0.39. So everywhere I see an O negative, I'm putting 0.39 next to it. Since we're talking about blood, not O negative, I'll put a 0.61. And I guess red and green make purple, so I'll make green be the sum of the outcomes. So let's see here. Not O negative and not O negative is 0.61 squared. 3721. And then let's go with the other one that we just did. 39 times 39 was 0.1521, so that's going to be O negative, comma O negative is 0.1521. And then now, your name again, sir? Mark. Now what do we do here for the other cases?
Are you asking me?
Yep.
We multiply the 0.61 to 0.39 to the bottom one, not a negative, a negative.
Yep.
And then multiply 0.39 and 0.61 for a negative and not a negative on top.
Perfecto. So we'll say O negative, not O negative, is going to be the product of those two, which is 3961. 2379. And because we know our commutative property multiplication, we know that not O negative and O negative is just the same thing as what we just did. 2379. If you loved your biology class, you could write it this way. I can't remember, was his first name Charles? Punnett? Okay. O negative, not O negative. O negative, not O negative. O negative, 0.1521, not O negative, or O negative, not O negative, 0.2379, 0.2379, 0.3721. And guess what? This guy better add to 100%. That's all your four options. So the tree diagram is a probabilistic way of representing what you might have seen in a Punnett square, or just using the different rules that you've learned. So either way, I want you to use graphs to kind of understand the world of probability. I'm going to lean towards tree diagrams, but in certain cases, if you want to represent it as a two-way table or a Punnett square, I have no major opposition to that. Okay, so then back to two-way tables. Two-way tables is rooted in probability rules. So I'm going to have my dear friend Megan help me with these. Megan's on the spot. probability that a randomly selected person, that a randomly selected respondent of all the respondents is a Midwesterner who agrees that global warming increased temperatures? So I'm looking for the probability of Midwest and agree. Miss Megan, what do we do here? What's my numerator, first of all?
The total, so, 1,009.
Whoa, whoa, whoa! No pressure, no pressure, no pressure. Numerator.
Oh, numerator, sorry,
Okay, so give me the denominator. What's the denominator?
the total of everyone.
All right, perfect. Okay, see, whenever people know stuff, but then when I call them, all of a sudden, like, anxiety kicks in. It's like, oh, man. All right, so that's the denominator. What about the numerator? Correct. 168. Midwesterner and agree will be these folks right here. And because I didn't give it a condition, you just go straight to that probability or that cell. .1665. All right, so again, what's different is that in chapter 6, I think in chapter 6 you might have stopped here. But in chapter 12, I'm going to focus a little bit more on the notation and the answer. Just be aware of that. But in chapter 6, you didn't see this little shorthand. Megan, you're not out of the woods yet. All right, we have an or question for you. What is the probability that a random selected respondent is a Midwesterner or someone who agrees? So Midwest or agree. How about this? What's my denominator?
The whole.
Okay, I can dig it. 1009. Okay, so I use what number? 732. And then now what else do I do with that? So the agrees are this guy, that guy, that guy, and that guy equals 732. I can dig it.
Sorry, I can't think fast.
Okay, go ahead. Okay, add 51 because that's who's left over for the Midwesterners. So 732 out of 1009 plus 51 out of 1009. Now, a little epilogue here is that I could do 732 over 1009 plus 219 over 1009 minus our good friend 168. But if you're clever, you can kind of see that 219 minus 168 is the 51 anyway. So no matter how you slice it, I get .675. That sound right? No. Yes, .7760. Yeah. So there are a couple ways of doing it. But again, according to that rule, you could do the probability of M plus the probability of A minus the probability of both. But in the two-way table, you probably can see some other shortcuts you can use. Megan, bring us home. She's like, no, I try to get off the bus. No, you must stay on the bus. All right. Oh, well, I got the answer there. All right. So Megan, the answer is there, but explain how we can get the answer from your perspective. So why is this the answer? How about that, Megan?
You just want everybody who's a Midwesterner, you don't want the whole population.
Yes. So it's out of the Midwesterners, which is the 219 people. And out of them, we had our dear friend 168. Perfect. So she didn't even need an answer. And this is just some math for you guys at 8:30 in the morning. So using the formula, 168 divided by 1009, that's going to be the cell divided by the grand total. And then you guys know back from high school, when you divide by a fraction, you multiply by the reciprocal. Reciprocal, that's a word you probably don't use every day. And what do you know? The 1009s disappear. And that's how it works out. I still prefer the chapter 6 way versus doing it with the reciprocal and the long way. Is that it? Oh, almost it. Okay. All right, so I will leave Megan alone. No more badgering. Is belief in impact due to global warming independent of region? Well, independent means this, right? The probability of A given B equals the probability of A. So B's behavior does not impact A at all. So what I'm going to look at here is it true that the probability of believing in global warming is the same even if you're from the South? I'll even try the Midwest. Is the chance of agreeing that there is an impact due to global warming the same as if you're from the Midwest? Well, let's check it out. So the South had 374 people. We'll put an S there. And then those who agree from the South was 262. .7, basically 70%. Okay, so that's going to be 0.70 is the chance of Southerners agreeing that there's been an impact due to global warming. What's the chance of agreeing overall? Well, agreeing overall is 732 out of 1,009. Which is 0.725. All right, so you can already see that these two percentages, 70% and 72.5, aren't quite equal. So they're probably not independent events, but they're not that far off either. So let's try another one as well. Midwest, put a MW. The Midwesterners is 219, 168, and then does that equal to 0.725? Let's see. Oh, we just did this, didn't we? 0.767. So let's write this down. Probability of A given S does not equal the probability of A because 0.70 does not equal to 0.725. probability of A given Midwest, or M, does not equal the probability of A. So that's what? 0.767 does not equal to 0.725. Now, they're close. They're in the 70s still, so it's not way off. But they don't equal to the marginal probability. So they are not independent, which means there should be some association. So no independence. And then, of course, we say that there is some association. Therefore, some association exists. And you can go a step further and say, like, well, maybe Southerners are less likely to believe that global warming has an impact than those from the Midwest. Maybe they're less affected by it. Okay. So from a notation standpoint, probably want to start here, then go here, then go there, then go with your interpretation. So when you're looking at your notes, like, what the heck did I write down? Maybe enumerating it kind of helps keep track of where you progressed. I was just trying to find blank space on my slide. That's all she wrote. You are not leaving. I cannot have you do that. Give me a few seconds to change gears. Okay. Moving on, chapter 11. So, what's about chapter 11? Well, 1 through 9, we basically say, okay, well, data analysis, data collection. Then 10 and 12, probability theory. And now the whole idea is that maybe the sample should reflect the population. That's one of the big key ideas, and so statistics helps us out with that. So here we go. You had some activity maybe 2 weeks ago about the random rectangles. You did that? Okay. I mean, we have these quirky things. I mean, some are cool, some are not. But thank you for enduring all of them. Right? So the TA collects an average from 5 students. He computes the average of the averages. Which data set has a larger range? So we're going to try and simulate that right in this class, right here, real life. Get out calculators. Okay? So I'm going to go ahead. Let's go to stat. And what I want you guys to do is go to probability, that's where it is. Math, probability, random integer. Remember that whole thing, random integer, right? Okay. So I'm going to do it. You're going to do it also. We're going to have some fun. Okay. Random integer 1, 10, how many? A random number of 10. Okay, we'll just do 10. And I don't care about repeats in this case. I don't care about repeats. So I'm doing random integer 1, 10, 10. Just give me 10 numbers. Okay? And then I want you to find the average for your 10 numbers. And I have mine. Remember, the average is just going to be moving the decimal place over because you have 10 numbers. No way, that's impossible. I got a total of 65, which means my average is 6.5. And my range went from 10, the largest number I had was 10, the smallest number I got was 1. So my range was 9. Now, let me get 5 volunteers, 5 brave souls. Jake, right? Okay, Jake, what did you get for your average? We'll say X bar sub J for Jake. 5.9. 5.9, okay? Let's go zigzag. Are you ready, ma'am?
I had 5.
5 on the nose?
Yeah.
And your name?
Mackenzie.
I love that name, Mackenzie. That's a good name. That's a good kind of, I'm Mackenzie name. All right, good. All right, yes?
5.2.
5.2. Your name again? Huh?
Jed.
Yeah. Ooh, we have J-A and J-E. All right, I need 2 more. I'm working my way back this way. On this side. Yes?
1.7.
Are you Clint? Right, that's what I meant. All right, so X bar for Mike. We have Mackenzie, and we have Mike. 4.7?
Yeah.
And we need 1 more. Going back further with the laptop. Your name? Brianne. Okay, I got a roster of all my students' names, so you guys are in trouble next week. 6.2. All right. Perfect. Okay, so which data set might have had a larger range? Your sample of 10 or the TA set of 6 averages? Well, I need 1 more, I guess. 1 more back behind Brianne.
4.3.
Your name again?
Lydia.
Lydia. That's one of my daughter's names. You're not my daughter. No. Okay, 4.3. I was like, she's supposed to be in school, but not at Ohio State. So there we go. So we have 6 ranges. So look at this. Which data set had the larger range? Mine did, right, by a landslide. I could assume values from 1 to 10, and you guys probably did 2 individually, right? Probably even got a 0. No, the lowest you can get is 1. There's no guarantee you would get the boundary points. My range was 9. What is my range for these averages? Not 9. Let's check it out. The range for the averages, the highest is 6.2. The lowest is 4.3. What's that, 1.9? Huh. The range here is 9, a big old whopping 9. Now my range is 1.9. So when you deal with the average of the averages, you have a more precise distribution, a smaller range of values. And it would be kind of funny, wouldn't it, if we had all these average of averages and someone came out with an 8.7. You must have did something wrong. Okay? So averages of averages tend to be more tightly distributed than just the individual random variables themselves. And you should have seen that in the recitation, but if you didn't see that, we did that today. Okay, so then, which would you expect to have a greater likelihood of occurring? A, you obtaining an average greater than 6 for yourself, or B, the TA having an average of averages greater than 8. Well, let's go back to the previous slide. It seems to me that there's a better chance of me individually getting a number bigger than 8. In fact, I did. I got 9 or 10. But I think it's almost impossible to get a number bigger than 8 for the average of the averages. So I'm going to say that this guy here is probably a better chance. So I'm going to say that the chance of having one number bigger than 8 is bigger than the chance of having the average being bigger than 8. So again, we're using our intuition to figure these out. Moving. So I had a larger range, and then of course I have a larger probability of getting a number bigger than 8. So then now you have some statistics, some samples, some populations, and so forth, some blanks to fill in. Your favorite thing to do in this class, but it's supposed to help you down the road. So sample statistics produce probability parameters. That's no problem there. I think I gave you that information. And then now, P for parameter, P with population, S for statistic, S for sample. So sample goes with statistic, and parameter goes with the population. So the sample mean is X bar, but the population parameter is mu. The average for 10 people is X bar. The average for the entire Ohio State body, student body, is mu. And then we have these proportions of all Ohio State students who support our new president, right, Dr. Drake. So that could be a proportion. And then, of course, a proportion of 100 students in today's lecture. Well, we don't have 100 students today in this lecture. Then we got 50. Then we got 60, 70. No, we got 60. All right. Then, of course, that's going to be our sample data. And then here's some notation that you can fill in at the top of the next page. You've seen this notation, X bar, X the line on top of it, so that's the sample mean, and of course population standard deviation is sigma. So the sample proportion is P hat, P dunce cap, as I call it sometimes. But we won't necessarily get to that until a couple more chapters. But it's probably good to just be aware of it. And then, of course, for standard deviation, you have sigma and S. All right, so let's see what we got here. There's a rule called the law of large numbers, and it tells us that the random variable can take on probabilities and things behave the way they're supposed to over time. Okay? So I might have mentioned this example before. My free throw percentage, right? I might hit 4 in a row, but maybe I'm a lifetime 80% free throw shooter in the backyard. In the game, I'm always like 70 or something like that. Okay? But if I hit 4 in a row, that's good. But over time, the law of large numbers says, not so fast, Dr. Baker. You'll probably go back to your 80% hit 4 out of 5 in the long run. Okay? So like when you flip a coin 10 times, you might get 8 heads. Do it 1,000 times. You probably get closer to 50%. So in the long run, your sample statistics behave the way they're supposed to, like the parameters dictate. Some more kind of theory. I'm trying to just walk through these a little bit so I can make sure we get to the real meaty stuff. X bar is unbiased, so it's not systematically off in any kind of capacity. All right, so let's see here. You draw observations at random. Yep. So X bar gets closer to mu as n goes to infinity. Oh, infinity. Careful, math stuff. Okay. So the more people you sample and the more observations included in your sample, the closer the sample mean should be to the population mean. And in our random data example, X bar for Baker was 6.7. But if I go back in time, the mean here for you guys is pretty darn close to 5. Let's see here. 5.9 plus 5 plus 5.2 plus 4.7 plus 4.3 plus 6.2 divided by 6, 5.22. So the average of averages was 5.22. So again, if I took more people, it probably gets closer and closer and closer to what it should be. Or if you guys sample more than 10 but 100, it should get closer and closer and closer to 5.5 or so. About 5.5. Okay, so we're saying that the same thing a couple times here. X bar will eventually get very close to the parameter mu. We said that before. And it can be done through simulation. We've kind of done that. You'll do that again on next week on Thursday in recitation. All right, and then now let's kind of go on to this piece. Oh, well, I'll go back. Maybe you guys still jotted it down. So, the statistic will eventually get very close to the parameter mu. Okay, so that's going to help you fill in the information that you need on that page. Right. Okay, so we'll leave this slide up there for a little bit. So the population distribution is the distribution of values of the variable for all the individuals in the population, and the summary distribution is for the statistic. So we saw this before in chapter 3. You had some mu, and you had a bunch of values that could assume. But now in chapter 11, you have some X bar and all the values it can assume. And we try to estimate or predict this behavior. And this is kind of embedded in one of your little statements there. The population distribution is for the individuals, in the population. And then, of course, the sampling distribution is the value of a statistic. So maybe that was kind of redundant. Moving and grooving. All right, so suppose that the X bar is the mean is SRS, simple random sample. And here's the kicker. The mean of the distribution is that. So we have here a mean mu and sigma ordinarily. But now when we work with sample means, X bar, the mean stayed the same, but now the standard deviation is changed. It is now the standard deviation divided by a factor relative to the square root of n. So what we're saying here is that when we're dealing with the sample means, the standard error needs to consider how big the sample size was in computing that mean. Where are my math? Who had a math 1150 here at Ohio State? No one? Okay, a couple of you. All right. Watch this. What is the limit, oh no, as n goes into infinity of this expression? 0, right. Now you may say, well, that's not required for this class, but let's use our practical knowledge here. As this number gets bigger and bigger and bigger and bigger and bigger and bigger, this whole thing is smaller and goes to 0. So statistically, the more people you sample, the more precise your standard error becomes. It gets smaller and smaller and smaller. And that's what happens there. When it was just me by myself generating random data, I had a big range. When you guys use, 10 numbers or 5 people, it got smaller in range. Okay? So that same kind of thought process continues. Just more things to jot down. And we will get to that major example. So as I mentioned before, X bar is unbiased. That's fine. And this is key. Averages are less variable than individual observations. That's key. And then to be even more predictable, more exact, large samples are less variable than small samples. So if you have a choice between 200 people in your sample and 20, err on the 200 if you can afford it, because you have more precise, you have greater precision in your results. All right, moving and grooving. So here's our formula for chapter 11, excuse me. And in general, the z-score looked at a value minus its mean divided by the appropriate standard deviation. And so here is this guy, no problem. We're back again with that. And now we use this formula. So in chapter 3, it was like x minus the mean divided by a standard deviation is z. Now we got to use this guy because the sample mean, we got to consider the sample size in there as well. And to be clear with you guys, I'm going to recommend that if you put it all in a calculator, offset it with parentheses for the numerator and the denominator, just to make sure we don't have any kind of data entry errors. All right, so bear with me. Let's get through this example. The first 2 parts, very critical to you doing your homework successfully. I know we can do it. Let's do it. All right. So, the first one, which is more likely, for one woman to be taller than 5'7", or for 100 women to have an average taller than 5'7"? I'm going to guess that one woman walking down the street being taller than 5'7" is more likely than 100 Ohio State women taking the average and them being taller than 5'7". So I'm going to go with that one. We've done that kind of thing. We've done that a couple times now. All right, so here we go. Let's see here. Here we go. So this is that. So the probability here, one woman, probability that X bigger than 67. Well, you do 67 minus 64 divide by 3 because we know that it's a normal distribution, 64 and 3. That's a z-score of 1.00. Look that up in the chart. Trust me on this. It's 0.8413. And you want the area bigger than this. So I would do 1 minus 0.8413, 0.1587. Okay, so I went through that a little fast, but I think you know how to do that. Or you can do normal CDF. 67, one big number, then 64 and 3, and it should be about the same answer. Either way is fine with me. Now here's the crux of all that rhetoric I've been giving you guys today so far. We go from having one woman, now we have 4 women. So with the 4 women, we got to look at the same approach, but one key difference, that their mean, so the chance that their average is bigger than 67, it starts out like the previous one. The number minus what we expect divided by the standard deviation of 3. But hold up, 3 divided by what? Square root of 4. When you see sample mean and a sample size, you got to kind of incorporate that somehow into your equation. Now we have here, what's that, 3 halves? So 1.5. So let's see here, 3 divided by, so we have here 3 divided by 1.5, right? Equals 2.00. Trust me, my friends. That's 0.9772. You want the area bigger than that. 1 minus 0.9772, 0228. So the chance for having one person being taller than 5'7", about 15% chance. For a sample of 4 women, the average being taller than 5'7", 2% chance. Weird. In the calculator, it's normal CDF, 67, some arbitrarily large number, 64, and then what? 4? Not quite. 3 divided by square root of 4. Put the whole thing in there. Okay? So whatever you have for your denominator there goes back that way. Let it sink in. I know we're in 856, 57 mode, but this is very critical to getting things moving forward for today or for the weekend. And then we'll finish up the other examples, and we'll wrap up 14 or 11, and we'll start 14.